So here, today's topic, data acquisition system, the supplemental problem set associated with this, which is problem 117 and 120. So what's data acquisition system? Yes?
Do we have a quiz at the end of class?
No, there is no
Quiz in today's. So the quiz will be on
Wednesday.
quiz number 10.
So I already
Make an announcement, I think, and it should be in Wednesday, quiz number 10.
So, data acquisition system, we already discussed before an introduction
About it.
So we said that whenever we use computer, that
We need to use it as controller.
So, when we discuss that the electrical signals can be data and it can be power, so also the data electrical signals, data electrical signals can be two ways, which is can be analog and can be discrete. So the analog most likely are continuous. While the discrete, it is something digital. Or digital can be continuous. So one example like computer, microcontrollers. One example of the continuous like some conventional like PI controller, PID controllers. So it's depending on the situation. Then we have also another types of controllers like digital logic, or we call it programmable logic controller, which is called, in other words, PLC, and there are other ways. But here let's focus about how can we make the digital signals. So whenever I want to use a digital controller or discrete controller, I need to convert this from signal or from, we call it the continuous to be discrete. So I need to discretize,
In other words,
discretize
the values
which is by using something called analog
to digital converter, which is
ADC. So which is converting all the values
to be in digital quantity.
And we have an reverse, which is digital to analog,
Analog
which is after
the
receiving the data to the computer. So I'm converting this back
to analog, then send it to the controller.
Okay. So we are also interested in looking at something called resolution and the sampling rates. So the first step, analog to digital converter. Let me assume that we have this sine wave. Okay. And I want to convert this to discretes. So in order to convert this to discretes, there is something matters, which is the number of samples per cycle. In other words, sampling frequency or number of samples per second. Those are matters. Why? Let's try to sample this. So sample this, which means take some discrete values, which is, for example, let's take a sample here, sample here, sample here, sample here, sample here, sample here. Then what the computer or will read it like this. Here, signal here, signal here, signal here, here, here. So that's what the computer will understand if the sampling rate in this case is similar to this. So, does this look like sine wave? Not really, but this is the ability of the device that I have.
It can understand it like this.
Okay. How about if I increase the number of samples? What will it be? It will be, for example, like this, 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 this. So is this one better? Yes. How about if I use a lower sample rate, which is this and this? Is this good? Yes. It's not that good. So we see that as much as we increase the number of samples, we will get the better performance. Okay? And how about this is like the principle of analog to digital converter, by converting this signal to be this signal. So let's assume that the controller do his job, and let's do this signal. So the output will be a specific signal. So let me assume that the outputs, so digital to analog converter, let me assume the outputs like this. And I want to convert this back to digital. So how will it be? It will be like this. Okay, so does this look like the original signal? Not really, but almost. How about if I increase the number of samples? This one is better, but still not sinusoid. How about if I increase it more and more? So we'll get also very similar, very near to this. So as much as we increase the sampling rates, as much as the signal will be very, call it, very similar to the original, or as much as we increase the number of samples, as much as we will not lose a lot of information. So when we do the sampling, we will use the information between here and here. So when we convert it back to digital, you will see that, oh, we're losing some information. So we are trying our best to not losing information. So we don't need to have some missing information here. When we have here, we have some missing information. How can we avoid this? By increasing the sampling rates. But can I do it infinity?
The sampling rate?
No,
Of course I cannot.
But it's depending on the technology
That I have and in the devices that I have.
So it's physical limitation, depending on what I have. So in order not avoiding sampling rates, so we need to have a high sampling rate. Or in other words, high sampling frequency of sampling. So to get the best performance, of course. So I think you might be aware of the videos, the quality of the videos, and also the computer screen or the screens. So you might be like in the last 20 years, you'll see that it was SD. Then we heard that about there's videos with quality HD, then full HD. Then we heard about 2K, 4K, and nowadays we are hearing about 8K. So what are those? Those are basically related to the, we call it the sampling rates. So when we look at the SD, you will see like the SD was 480 kilobits. Then HD 720, full HD 180 or 1800, etc. So you'll see that this number is increasing. This number is related to the number of samples. So the number of samples, if it's high, then we will get the right image. So we can look at here. So let's assume, for example, this is SD. So does this look like the sine wave? Not really. That's why the SD is not, sometimes it's not that good quality. Then the HD, we'll see, we'll see that the picture is kind of better than the SD. So it will be almost similar to the original. Then, for example, in 4K, for example, we see this kind of stuff, and so on. So the technologies keep growing and will continue growing. So why the people didn't invent 4K in the beginning? Because of the limitation. So in the past, we didn't have that technology or that ability to make a very good product, or we don't have the ability to make it commercialize with lower costs, with low values. So right now, they are trying to improve the technology as well as make it commercial, which is very cheap, so it can be affordable. They don't want to make it like we can create higher resolution while you need to pay a lot of money.
So we need to make it commercialized. That's the word, commercialized.
So the resolution is associated with how can we increase the number of samples. So if the number of samples are low, which means we are losing information. If it is high, then we are getting more information. Okay? So resolution most likely also will be when you look at, sometimes when you go to the computers systems. So when you look at the past, the last 25 years, you'll see that there was some computers in 16 bits. Then we hear that there was
a computer 32 bits.
Then 64-bit operating
System 64 bits.
So what are those? So most likely when we say that, or there was also computers in the past 8 bits.
I still remember that.
So it is 8 bits. It's basically, since we are in
machine
languages,
which is it can be
binary,
which is
0 or 1. So it can be 2 power 8. Then they invent 16-bit 2 power 16. Then right now we have two systems, 32 and 64, 2 power 34 and 2 power 64. So of course when you ask what's the better system, the best performance,
which is 64.
Which is we have a lot of possibilities
to do a lot of languages, and it
can handle very high volume programs. So the resolutions is very important as well. So as much as we increase the number of bits, then we get the best performance. So in the resolution here in this course, we need to focus about like the number of bits, and we need to focus about it's called smallest detectable voltage change. This can be also very important in instrumentation measurements. So you can see how much my device accurate. If my device can detectable as low voltage as I can, then it's as accurate as I can. If it can handle higher or couldn't handle very low values, then it couldn't do, it's not that accuracy. So sometimes when you look at the devices, the accuracy is plus minus 1 volts, or the accuracy plus minus 1 millivolts, or the accuracy plus minus 1 microvolts. So what's the best device? Of course, the accuracy plus minus 1 microvolts. So we are trying our best to make it as low as possible. So to get the best performance, how can we get as low as possible? By we have a V full scale, we have 2 power n. So V full scale, most likely it is something depending on the device specification. Since I need to make delta V as low as possible, I need to increase 2 power n, which means since still here we need to increase n, which is the number of bits. So as much as we increase n, then we'll get small delta V. So what's VFS? What's n? N is the number of bits. Increasing the number of bits will improve the sensitivity, or the smallest detectable voltage, in other words, sensitivity. And V full scale, it's related to the scale. So we can say that this device can handle plus minus 10 volts, or can read plus minus 10 volts, or can read plus minus 1 volts, or can read from 0 to 5 volts. It's up to the device. So V full scale most likely will be the upper value minus the lower value. Okay? So let's assume that we have a range from 0 to 5. And we have the number of bits equal to 2. Then we can say delta V equal to V full scale, which is 5 minus 0, upper minus lower, divided by 2 power 2. So it will be 5 over 4. So it will be 1.25 volts. So what does this mean? This means my device can read value 0, 125, 2.5, 3.75, and 5. It can read only those. How about if the value is 1? It will not read the 1. It will read it either 1.25, which is the nearest value to it. So let me assume that I have this range. So my computer will not understand this. How will it understand if my computer is 2 bits? It will understand it as this. This value, this, and this. So the dots will understand the dots. Because it didn't have the ability, there is a limitation, didn't know what's going on between these two. So anything happening between these two will make it or will approximate it or round it to the nearest value. So that's how my device is doing. So we can see that we are having losing some information. And we will convert this like to digital. So it will be. So that's how we'll read it. So we'll have some errors, some missing information. So this not like this, but it's very close. And when we increase the number of samples or decrease delta V, then we will have many points. Then we have many points. We will have very signals that's very close to the origin. So again, this is also the idea. You can imagine that how's the video quality looks like if you imagine like this image and this is the real image. So this image is kind of distorted, not exactly to the real, and so on. Okay? Any questions? So here in this lecture, I'm trying to focus more on the concepts, while the formulas, you can just write this formula in your note sheets, and you need to know how to apply it, and that's it. So if you see like a test in the final, find the resolution, or find the smallest detectable voltage, just apply this formula, and that's it. But here I'm trying to focus on the concept, so how we are using this in real life. Okay, let's assume 3 bits data acquisition system and V full scale equal to 8 volts. How can we do some analysis on this? So we can say that, or let me assume that V full scale, not V full scale, or the range between plus minus 4 volts. So we can say that V full scale equal to 4 minus 4, which is 8. And number of bits equal to 3, therefore delta V equal to V full scale over 2 power n, which is 8 over 2 power 3, then it will be 8 over 8, which is 1 volt. Which means that my computer can detect only 1 volt range. So we can say, like, this is the table. So this is, it can read 1 volt, 2 volts, 3 volts, 4, 5, 6, 7, 8. That's how my computer can read it. Or actually, since I'm in the negative, okay, I'm sorry. Here is negative 3, negative 2, negative 1, 0. I'm sorry about this. 1, 2, 3, 4. Okay? So, how can the computer understand this or translate this? That's how it can read. It can read these values. How will this be translated to the computer language? So most likely, since we have 3 bits, this bit 0, it's weighted 2 power 0. Bits 1 weighted 2 power 1. Bits 2 weighted 2 power 2. So for negative 3, if you remember, you might remember the truth table. Something's called the truth table, which is started. Yes.
Why can't it read negative 4?
In this range, we can say that the negative 4, it can be, let me see, it's supposed to be here. Let me check how many, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I think the negative 4, there will be, if there is no readings, then it will be negative 4 in this case. So no values. So the increment is 1. So when there's the first step, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. So the truth table says here 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. This is the truth table. So this is bit 0, bit 1, bit 2. So whenever there is 0, 0, 0, it will read as negative 3, or negative 3 will translate it to 0, 0, 0, negative 2 translated to 0, 0, 1, and so on
until
4
we'll
will translate it
as 1, 1, 1.
And actually,
I
I
think
think
the
the range,
range, yeah, that's the point.
the range
Here, actually, in real life, this is supposed to be -4, actually. Sorry about this, -3, -2, -1, 0, 1, 2, 3.
that's
That's what it's supposed to be.
While 4, it will understand it as overflow. So which is something that's kind of advanced. So while 4 is not included, it can be included, but it will be overflow. What do I mean by overflow? It will be like 1, 0,
0, 0.
and the 1 here cannot be understandable by the computer. So there will be, you will see some error signals
Let's say it's overflow.
So here, -4 is
It's already
included.
here, -3, -2, -1, 0, 1, 2, 3.
And in 4,
It will be overflow.
These things are
No,
in different codes
it's called digital logic.
So here I just want to show you that how is the stable. Then we will say as delta V gets smaller as
System
goes more accurate. Now I want to discuss about the sampling rate. I already discussed about the sampling rate before. Like I said, that here, as much as we increase the number of samples, the best performance. So how can we, or let's look at something that's called Nyquist sampling. So Nyquist sampling theorem says that the sampling rate must be at least twice the highest frequency. So when we have a signal, look at the highest frequency, we will say that F sampling should be larger than 2 times F highest. And there is a Nyquist rate which is the criteria, the minimum. It's exactly twice. So F sampling should be 2 times F highest. This is the Nyquist rate, which is the minimum. What about if my sampling frequency is below than 2? If my F sampling below than 2 times F highest, the highest frequency, what will happen? We will have some misinformation, or something we call it aliasing. So aliasing is misinformation. Which means the image will not be clear at all, or part of the image will not be clear. So the image will not reverse the reality. Like what? Let's assume that this is the sine wave. Let's assume that the frequency in the first case is higher than 2 times the highest, so which is, I have these. When I want to transfer this
to the
back to continuous, it will be almost the same
to sine wave.
How about at Nyquist rates? At Nyquist rate, I have 2 samples. So what will I have? I will have like this, like this. It's not sine wave, but actually it can give me an indication this part is positive, this part is negative. It can give me some information. Like the image is not clear very well, but it can give me part indication what the image is. But if the aliasing is below than 2 times, so I will have this. Then it will understand it like this. And this, of course, not this. It will give me image that's very, very unclear. And it's not the reality. So this thing we call it aliasing, which means some information
will interact with each other, will enter each other
to get a very
distorted information and
missing information. So this will sometimes will be harmful if you have some control system and we have some aliasing, especially in some sensitive equipment. It will be dangerous. Dangerous in controlling. So you have incorrect, for example, incorrect speed, or incorrect important information. So this is not good for the system. So what you need to know, just in this topic, you need to know this relationship delta V equal V full scale over 2 power n, and you need to know the Nyquist minimum frequency 2 times f highest, and f sampling should be larger than 2 times f highest. That's it. And the other things that I explained in this course or in this lecture, it was just information that's just to understand what are those. Let's look at this example. So here, the output power system probe is plus minus 1.5 volts, and we have 16 bits ADC. So here we ask us to determine the we have some devices with these ranges. So which range should I use to cover 1.5 volts? What do you think?
Plus minus 2 volts.
Plus minus 2. So why I'm not using plus minus 1? Because 1.5 are not covered by plus minus 1. So that's why it's not. How about plus minus 10? Plus minus 10 is already covered in plus minus 1.5. Why I'm not using it? Or actually I can use it. But why is not recommended to use it?
Increases resolution.
Exactly, because it will decrease the resolution. Because we have delta V equal to V full scale over 2 power n, which is here V full scale over 2 power 16. So if V full scale equal to plus minus n, which is 20, it will be higher than 4 plus minus 2, 4. So it's recommended to use this. So use this. Okay? So also use this covers plus minus 1.5 and low resolution. Resolution, okay. And how about here determine the range? So substitute in this formula. So delta V equal to V full scale, which is plus 2 minus negative 2 over 2 power 16, which is 2 plus 2, which is 4 over 2 power 16, or in other words 4 over 65 536. Then the answer will be 16.04 microvolts. That's just straightforward. Apply the formula. And the last part, if the signal has the frequency content 60 Hz, 180 Hz, and 30 Hz, what's the lowest acceptable range? Or maybe in the test, what's the Nyquist rates? It might not be asking what's the lowest, what's the Nyquist rates? What do you think?
600.
2 times F highest. So F Nyquist 2 times F highest. What's the highest frequency do I have? 300. So 2 times 300, which is 600 Hz. That's it. So when you see these kind of questions in the test, they should be straightforward. Determine ADC, delta V, which is the formula, V full scale over 2 power n, and determine the Nyquist rate 2 times the highest 300. And that's it. Any questions? Okay, so that's it.